Welcome to International Institute of Information Technology, Bangalore, and thank you for making it here on this rainy day. So this is our workshop, hopefully the first of its kind, automotive workshop from software to sustainability. I was thinking in the morning we could have subtitled it from Outer Ring Road to Electronic City. So yeah, and I think whoever has made it from the city are real heroes, and I must congratulate and thank you. We also thank Professor Debabroto Das, our beloved director, for making it here. He has a very long day ahead, we know, and still he snatched out a little bit time for spending with us. So before we start the proceedings, I would request him to come and say a few words and get us started.
Thank you, Professor Sujit Chakravarti and Professor Ronald Haas for organizing this workshop in IIIT Bangalore, and very good morning to each and every one of you, and warm welcome to IIIT Bangalore campus. And I am sure this topic is very interesting and go close to my heart, even though I work on only the communication and networking protocol part, but now the automotive without communication is no more there. Past automotive has changed a lot, which you all know. So I'll be talking couple of points on this issue from technical point of view, that there are a lot of things, huge change and happening in the automotive industry itself. It was previously there was only electronics part was there on some small control dashboard with a little bit of metering, gauging the engine conditions, oil conditions and all. But now those things has gone as a very much compulsory part of it. Now the automotive is moving multiple direction, like driverless cars to your inside, like called comfort zones for the who is sitting inside, and every seat and every area is now different attention to the particular person who is sitting there, his comfort with respect to AC, entertainment and direction, thought process and all, and plus navigation. And if I look at the whole automotive, it is now more and more electronics, which you know, and all those things. But there is a one catch, which is a big problem in front of us when I am talking from my automotive and with respect to the software, and sustainability is another bigger issue, but from software point of view. So now we are under tremendous research challenges. So there are a lot of that how to reduce the delays in the automotive, in the communication point of view. It was when we are in the 4G, you used to say hello from here. The delay was given when the standard was 150 millisecond. But now in the 5G coming in, now the people are talking about in the driverless car less than 10 millisecond. So it's 1 by 15 times less. So like that, so there are a lot of some 1 millisecond, 2 millisecond. So if you are talking about the millisecond and the software of the automotive is also involved for this communication, then, and as we know, the hardware and software, hardware is much faster than the software. So how to make those kind of design and failure, no failure kind of things of the software and communication much faster in the embedded and all. So, and also the sustainability of those vehicles while it is running. So these are the things which already in our card, which we are working in the labs here with the software engineering team and all. And so I look forward those kind of nice discussions of different areas, starting from of the automotive industries. And I have another dream in my mind, which I shared with Professor Roland Haas 1.5 years back, and with the Professor Sujit also a few months back, when we developed a software engineering center here with Professor Chandrasekhar. So that we should have an automotive center of excellence, and particularly in these topics, software. And also one thing which will definitely come in discussion, I'm sure, because Professor Roland and Sujit is here, called security. So it will be 3 S. Software, sustainability, and secure software and sustainability kind of thing. And he has written a book on that, and 2 books on that. So I'm sure you will be definitely showing them your book. So that is the thing. So I wish you a wonderful time today and next till the afternoon, and wonderful discussions. And also at the end, any suggestion, please give us. And we are heading towards that direction slowly. Maybe within 6 months or 1 year, we'll make a good research center on automotive, the areas wherever we focus, where we can complement industry and academia of different places. Thank you again for coming here, and thank you, Professor Sujit, for so calling me.
Thank you so much. Wonderful, wonderful. Okay, thank you, Professor Das, for the good start to our workshop. And that's just tip of the iceberg to the support that he and the institute in general has provided us to bring this all together in a very short time. I think really thankful to the entire IIIT system. So with that, let me just introduce to you our institute, because many of you are probably visiting us for the first time, right. So as you can see, we are spread over about 9 acres, which makes us a pretty small campus, right? And this is where we are. Since you are here, so probably this slide is redundant. So, right. So this is about the academic programs that we run here. As you can see, we have PhD and MSc Master of Science by Research. So these are 2 research-directed programs. Apart from that, we have our course-based programs, which are MTech, Integrated MTech, MSc Digital Society, which is an interdisciplinary program. And then we have a number of collaborations with other organizations, and we provide continuing professional education to working professionals, right? So yeah, so this is, I have a link from that population distribution, but let's let it go. So we are pretty active on research, and we distribute ourselves, the faculty members here distribute themselves under these 7 heads, which we call as research domains. I work in software engineering down there, but there are these other computer science, data science, embedded systems, NCS, network communication and signals, IT and society, which is basically a combination of information technology, social sciences and humanities, and then we have mathematics and basic sciences. We also try to align ourselves in terms of business verticals or industry verticals, and have tried to create the centers of excellence. MINRO is Machine Intelligence and Robotics, Center for Data Sciences. CITAP is again a center for excellence for IT policies, public policies. And we have EHRC, which is basically about health research. Okay. And we have plenty of collaborations running with various external partners under these centers of excellence. And this slide is for innovation. This is particularly for those of you who come from an entrepreneurship background. So we have a support ecosystem for having entrepreneurship and startups here. So a number of mechanisms to help you get started with your entrepreneurial ventures. So that's it. That's it from my side. I think I would like to welcome you once more to our campus, and look forward to having a great exchange of ideas and conversations with you today and going forward. So with that, I would like to hand it over to Roland, who will introduce the workshop, today's agenda, and other technical things.
Thank you very much, Sujit. And thank you very much, Professor Das, for the nice introduction. Welcome, delegates, participants, colleagues from IIITB, and students. So it's a big pleasure to have you here. I would like to, set a little bit the stage regarding what we want to achieve in our workshop. And let me take you through a few slides here. So just a brief look at the agenda, what we are planning today. Of course, we are behind time a little, so that puts a little kind of pressure on us to be innovative, how we do our time management. But what is very important today is the networking part of that. The whole workshop is under the umbrella of academia meets the industry, and that's really what we would like to have, and the time also to actually do our discussions on these topics. So we have our introduction to the workshop right now. We will have a keynote speech that is coming up by Professor Dr. Soresh Nagesh on digital twins, our coffee and networking break that we'll have, but somehow we need to see how we can organize it in the best way so that we can do the networking and still save some time. Then our panel discussion is very important. The panel is then later on also open for the discussion with the audience. So we also want to keep it very interactive. And we will have, and that's one of the main points here, our workgroup sessions where suggestions come from the delegates, and we then will allocate some rooms where the workgroups can meet and discuss. And there will be a little presentation at the end of that, what type of discussion topics you had and what are the results of your work group. We will have our lunch break, and after the lunch break, the work group findings will be presented, and we try to close in time, because I know that you also have to travel back, so we don't want to overshoot much on the time in the afternoon. Now let me tell you about what our workshop really addresses. And I give you one example here regarding Volkswagen. I used to work with Volkswagen in a project on the modular electrification construction kit in 2018. And Volkswagen was structured like that. You had the factories, which were capable of doing 6,000 internal combustion engines a day. And the most prized products was something like this, the Bugatti Veyron, with a kind of specification that is unimaginable for a combustion engine. And we had also some groups coming in that were actually kind of doing the maintenance work for these Bugatti Veyron there at the place where I worked. But that is kind of a little bit of the past for Volkswagen, because what's happening now is a major transformation into a company that is into electronics, computer science, and electrified vehicles. So what we have here now is that we have a fully electrified product line that is coming up. So we see the first of those products already out there. Then we have a domain that is connected. So all those vehicles will be connected to the cloud for new services, connected car services. Volkswagen also goes into the supply of energy and into charging under this brand name, for example, Elli, where they provide charging solutions. Then they have bought back the rental car service, so they also kind of take their stake back into the mobility services. They are transforming themselves into a software company, and you have heard maybe that this was not that successful that Herbert Diess planned. That's the reason why they have now a new CEO, Oliver Blume, because building up a software company within Volkswagen is not that easy than it sounds. So the name of that is the CARIAD Group. Then autonomous driving, Volkswagen invested into startups. Here you can see that they believed that the innovation would come from the startup scene. So they invested into Argo.ai together with Ford in order to be able to leapfrog the autonomous driving activities. And what is also very important, the vertical integration. So Volkswagen invests into batteries, and they're planning to build up gigafactories for the battery setup. So some of the plants that you have seen there in front, they will be converted to battery gigafactories. And all that is integrated through a modular electrification construction kit, which I also worked on in that time, which will be not only for Volkswagen, but also given to other companies as a platform to get economy of scales. To give you another example of this transformation process, I have a chart here from Mercedes, and this is the Mercedes E-Class, so one of the very important brands of the Mercedes passenger car group. And what you see here are the different models and when they were introduced under this code name W in the different timelines there here. And then you see three charts. One shows the number of ECUs, that's the solid line down there, so the number of ECUs going up, but you also see they're not steadily increasing anymore. because now we have different architectures, vehicle computers, for example. But what is also very interesting is the non-solid line there in the middle that shows you the number of signals. These are signals on the CAN bus or on the computing network of the car. And you see this number has gone up quite significantly, no? Really reaching about 10,000 different signals on the bus system. But most impressively is what happens with this exponential growth of the bandwidth. And that's actually the challenge for the automotive industry, because we not only talk about a mechatronic system with different signals that has to work in real time, but now we are talking about a system that also has to integrate all those streams, bandwidth-driven data that comes from the connected cloud, that comes for autonomous driving, self-driving features, or from the infotainment system. And this is where the challenge comes up and where the electronic and software architecture fundamentally changes, because it has to deal with this high bandwidths and these bandwidth demands which are coming up. When you see on the right side, that's where the architecture completely changes. Daimler has and Mercedes decided to hook up with NVIDIA as a vehicle computer infrastructure, and then the architecture changes in terms of you don't have so many ECUs, you have centralized architectures, vehicle computers, and you handle the bandwidth from the connected car as well as the real-time behavior for the control systems in the car. So that's where I would like to show you the final slide before I hand over then to our first keynote speaker, how we are planning the workgroup sessions. We will have a pinboard kept here in the hallway. Then whoever wishes to propose a subject can put up the subject for the workgroup session. So these are topics you would like to have been discussed in the group. And then we'll actually, deadline here at 11:30, find out what are these topics for the break group sessions. We'll allocate the rooms, build teams, 4 to 5 people, depending on how many topics we have. And then we will run the breakout sessions starting at 11:45. And finally, the breakout sessions, there will be some in the one who has proposed it and wants to drive the breakout session can then summarize after lunch what are the findings, what you have seen and discussed in your break group session. So at that point, I would like to hand over to Professor Dr. Suresh Nagesh. And while he is connecting his system, I'll give you a little bit introduction to him, but he has such an impressive CV that if I would start reading it out now, I would take maybe half an hour, so I will just give you some highlights. So especially as we also have worked together, Dr. Suresh and myself, we worked together in Daimler when I had the chance to come over from Daimler in Stuttgart to here, India, late 2000, 2001. And he at that time was working with GM, the GM R&D Center. So I told him, have a look at Daimler. Does it make sense for you to, head a group and start the practice in computational mechanics? That he did, and after that, a few more interesting activities working with the engineering service industry. Then later on, coming from the computational mechanic background, Dr. Suresh became a professor at PESIT for computational mechanics. They are also very instrumental in the CORE activity there, Crucible for Research and Innovation. And one of the recent activities, and that's what he also will report about today, is that he is now starting and has started a engineering service company and an electric car or car company that is coming up with a new model here under the brand name Quantum. So, Dr. Suresh, the stage is yours.
Good morning, everybody. In fact, actually I should say that I was visiting IIITB many years back when Dr. Shadgopan was heading this place, because he was my teacher at IIT Kanpur long time back. Okay, we belong to the first 4-year scheme, 81 to 85 as undergrads, and he was one of our teachers. So I'm happy to be back again at IIITB. And me and Roland know each other for more than 20 years. We worked together, started the Mercedes-Benz Research Center in Bangalore, And today we are happy that it gives life for a few thousand people, right? We continue to work with Mercedes. I'll show you some of the activities we are recently involved in, and I think you should come to our lab now. You can see the two test rigs. You have not visited us for some time. So, and also I thank IIITB and all the organizers for providing me this opportunity. I'll be talking to you about digital twin. In fact, we wanted to integrate academia with industry in our country. My PhD is from University of Pennsylvania in US. So we were in US with the Ford research, Daimler research, and then of course we came back to this country, and we want to contribute something back. And therefore, about few years back, our life on digital twin started actually with Siemens. In fact, Siemens considered our group as the only group for doing this sort of research, and we developed an actual digital twin, for Siemens motor applications, and which is going on Siemens motors starting this year, which we are really happy about. Most importantly, I'll talk to you more about the challenges when we try to bring AI and ML from the IT industry to the engineering domain. Okay, so our group is a multidisciplinary group, combo of everybody from very top computer scientists to electronics people, and of course mechanical engineering. Because today you cannot call yourself really as an AI engineer. You need to be a multidisciplinary person too. And as Roland was trying to say, everything is now somehow controlled by electronics. So it is better for all of us to have some knowledge of, and how to integrate that and make the product actually work. Okay. The critical thing is to make this product and make it work, and that's where all the complications and challenges comes in. And each challenge is an opportunity. And so most of our focus these days have been on the digital twin technology. And I will also give you some glimpses of what we are trying to do as far as Mercedes is concerned on the digital twin side, and where the automotive industry is looking at from the digital twin perspective. Okay. With that background, let me start. And you can stop me anytime. Okay. This is a very short presentation, but I would like to interact more, take more questions, and little knowledge that we have gained over the last 5-6 years, we would like to share that with you. Because talking to a pure computer science person, there are some challenges. Talking to a pure electronics person is another challenge, and talking to us who are somehow all-rounders is a different thing altogether. Okay? Because we come from the industry. So we bring a different perspective to the system, and we have seen the automotive industry way back from 92 onwards, last 30 years. A lot has changed from how we were doing things to how they want to do things. So somehow we also have to keep up the pace with the learning, and every day I learn something new. Okay. So in terms of digital twin, if you ask an ordinary person and say, okay, what is digital twin? Next second he will say, no, sir, I will get a million sets of data points, I will do a very good fit, and then I will make some predictions. You can talk and you can find out. This is the general answer that we get. This was the same state of affairs when we started about 5.5 years back with Siemens right here in Electronic City. And we were talking to our German colleagues and then the Indian R&D people. And everybody was asking the same question. So at that time, we also defined digital twin in exactly the same way. Okay? And then we did a lot of brainstorming, and we said, that's not really what it is. What people today are looking at are smart systems, which can take decisions on their own. And then we said, okay, where do we start? On one hand, a lot of us have been with the computational mechanics domain almost, I would say, from my 6th semester at IIT way back in 84 to date. 38 years of hardcore computational mechanics things, a lot of physics-based problem solving. And now you see, then you have a set of computer science people who are really good in what they are doing. They are AI, ML experts and things like that. Then you have the electronics person in between who says, I can integrate everything. The idea is that can I develop a device which by itself can take data in situ from a system? It could be any system. It doesn't have to be necessarily a particular application. That is how we started thinking about the concept. And then how do I integrate this computer science person who doesn't understand a motor, or an electronics guy who doesn't want to even start the motor? Okay, this was our initial problem. That I will show you the lab setup also. So we decided the only way we are going to work is we are going to come together. There's no other way we can do it. So we said we'll come together. And then, so we started putting things down. So what are all the different activities that will be involved in order to create a digital twin which is workable? Okay. So we said on one hand we have to do a lot of computation, which is basically what we call a CFD, etc. A lot of vibration simulations, temperature simulations, electromagnetic simulations. That itself is a huge activity. On the other hand, I had to build at least a test rig to gather the data, and then build sensors to gather the data, whether it's a vibration sensor, temperature sensor, current sensor, all these things. And then I had to integrate this, and I'm getting data from that one. And my computer science person should be able to understand this data, because all decisions need to be made on physics-based responses. That means I have to look at the response and I have to take the decision. So whenever I was not allowed by Siemens to talk publicly about digital twin, but now I have been given a little bit of permission to do that, because this is a highly competitive field, and their competitors, ABB, etc., are also trying to develop something similar. So to give a very simple example, okay, it is like if you go to get your ECG done to see your heart, what happens basically is that 4 probes are put on the body and you get a signature, and a good cardiologist will say, okay, fine, your heart is doing fine or not doing fine. That is in some sense a little bit of data analytics that is done, but it's not real, but my device is not a digital twin. Now imagine that one of those probes happened to also get connected to a million sets of data points, which is very easy in the medical domain to get. And then I will be able to say, okay, this particular response that I get corresponds to a set of responses with a level of probability. So there's probability, statistics, reliability, everything that is getting integrated into these digital twins. And then with certain level of probability, I'll be able to say, okay, your heart is doing fine, not doing fine. So you are doing the diagnosis part. But that's not the end of the story. So that means I'm able to find out if the system is performing the way it should, or it is not performing the way it should. That means I'm trying to identify the defect in the system in situ, as and when it is functioning. But that's not the end of the story. The next question Siemens asks, so what if there's a defect, what do I do? Can you tell me, can this live for some more time? We call that as remaining useful life. That's where the machine learning part comes into picture. And algorithms that are available on the machine learning side could be used to actually compute the remaining useful life. Because at the end of the day, you're driving the car. I am able to find a defect in a particular system of the vehicle. But will I also be able to tell you that you can drive maybe another 10 kilometers, 20 kilometers down the line, where you can find somebody to actually support you? So, and then the question is, can it be repaired? Should it be replaced, etc.? This is where all the edge devices are now being connected together to completely provide a digital twin for the entire life of the product, from material to the product through the process. And this is exactly what they are looking at. And in fact, I welcome you to our lab, and live we will show you the digital twin development for the transmission of Mercedes that we are doing right now, digital twin for the lubricant flow system, as we call it. And very shortly, we'll be working on the digital twin for the e-motors for the first time on the globe. Okay, so you didn't hear me talking about it, but this is something that we'll be doing. So we'll be very happy to show you what we're doing there. Okay. And of course, for Siemens, we continue to support on the rotor dynamics activity, which has got attention by the buy of Indian Air Force and Navy. As of yesterday, I need to talk to you, Roland, on that one. So on the gas turbine side, they want digital twins for the gas turbine of the naval systems, which itself is a fairly complicated problem. And what I'm trying to say is that, so you need to have a knowledge of the system first. Okay, what is the system that I'm talking about? What are its functional characteristics, performance characteristics? What is that I'm really looking at? What can go wrong? And if something can go wrong, can I be able to also tell you that ahead of time, can I tell you that something is going to go wrong? And if it's going to go wrong, then what do I do about it? This is the fundamental philosophy of the so-called digital twin, which is all, it is up, and whatever you develop should be so modular that I should be applying it to any system, be it a heart or be it a machine. Because I'm looking at the data, but I'm interpreting the data differently because the system is different. But by and large, all the hardware and software that is developed should be able to address multiple systems. Okay? And this is also the challenge that we face. So this is an integration of all disciplines in that sense. Okay, so basically this involves simulation, upfront data collection from the sensors, integrating the in situ data with the simulation data, and then trying to do both diagnosis and prognosis. Ultimately, I need a system which can take a decision on its own and also provide me inputs about the state of the system. Okay, I'm trying to make it very simple. I know there's a lot of technology behind it, a lot of hard work has gone behind it, and a lot of very brilliant people support me on these things. So if you have any questions, please feel free to talk to me, and then I can. So AI basically we have used for the diagnosis part to find out if there is a problem, or if there is a problem, what is the problem. And the ML is what we have used for basically trying to find out the remaining useful life of the system. And till date, we worked a lot on physics-based analytics, looking at the responses. For example, for the motor, we looked at the response in terms of vibration, in terms of temperature. We thought more than one parameter is required for decision making. It's not just I decide the state of the system using just one response, which may not be very accurate. So to improve the accuracy, we look at many different physical responses. Okay? And then later on, we found that for certain cases where, for example, temperature is an issue, I just cannot take the temperature from outside the system. I'll talk about that. What are the challenges? Because the challenges are really the opportunities for us to work on. The whole problem in this, let me tell you, the biggest challenge that we faced is that if you take any sensor that is put on any system for data acquisition, all the sensors are put outside the system. Even the probe I was talking about, the AC, is put outside the system. But the real problem is inside the system, right? So how do I take the data from outside the system and be able to reliably predict what is happening inside? This is a crucial problem in this whole thing. One of the biggest challenges that's there in the development of digital twins for any system is to fundamentally understand how to take this data from outside the system and be able to reliably predict what is happening inside. Okay, this is a very serious challenge. And then, so this is one challenge that we had to address. The second challenge that we had to address is how many sensors can we put on any system? Hardly any. So the number of data that I can get out of any physical system is probably a couple of dozen, not more than that. If I get about 30 data points, it's a lot. But if you talk to my computer science friend, first thing he will say, no, I need million sets of data points. Where do I get million sets of data points from an engineering system? Absolutely impossible. So we started working on the technology called sparse data analytics. How do I take minimum set of data points, but be able to still reliably predict what is happening, So that is when I remembered one of my professors at U of Penn who defined engineering. So engineering is the art of doing things approximately right than being exactly wrong, okay? So all of us, our CV is that. So if somebody asks me, what is your CV? I said, I'm an engineer. So define engineering. So it was a fantastic definition which I don't forget in my life. And I talked to Roland on this many, many times. Okay, so he also asked me when we actually met in US way back in, I think, 98. Okay, and then he pulled me into Daimler in 2003. And then from then on, we use this term. So engineering is the art of doing things approximately right than being exactly wrong. So English is such a beautiful language, and just think about it. That's exactly what all of us do. Everything is an approximation, but how approximate is the real question, right? So this digital twin is also an art of approximation, because I have only so much of data that I'm getting, but I still have to make some sense of this data. And this is exactly where we started working on sparse data analytics. How do I take minimum set of data, but be able to reliably predict what is happening? This is where probability, statistics, reliability, everything comes into picture. And so the key challenges, therefore, when we try to develop this digital twin, our number of data points that I have is extremely limited. I cannot have infinite sets of data points, especially on the engineering system. And number two, as I said, all my problems are inside the system. The bearing is inside the motor, and the bearing is going to fail. But my digital twin should be able to take data from outside and be able to say that my bearing is failing, for example. And this is really where the physics-based analytics comes into picture. I look at the vibration response. So if the first peak is picking up, then I say there is no problem with this system. If the second or third peak is picking up, then we talk about different misalignments, because typically these are the defects. So first of all, I need to understand the system. I need to understand what are the possible ways in which this can fail. These are basically the defects, and those are the test cases for me, therefore. But I cannot build, one test rig for each test case, which is super expensive. And this is the reason where the CAE CFD comes into picture. A lot of numerical simulation with variety of defects can be easily done. But I have to validate that at least with a few test cases. That is the reason why those test rigs are built in the first place. Some design of experiments are conceived and done, validated, and therefore all the models which go into the physical digital twin are basically semi-empirical models, which are combination of test and simulation. So suddenly you start realizing that this is a pretty complex, science, art, everything coming together. Okay, so typical process is therefore numerical simulation on one side, gathering in situ data, and then there is a third challenge that we also face. Now I developed this digital twin, which is actually a physical device, and I put it on the actual vehicle, for example. So in the lab, I can only capture some amount of possible ways this can fail. But when I put it on the real vehicle, or let's say I'm working on a digital twin for an aircraft engine, and this sits on an aircraft, it has to be highly reliable in terms of whatever data that it is gathering, inference of the data, and providing you, with a decision. Now, because it's a security issue, safety issue, so this can just, if my inference is not correct, then the whole flight can come down. And this is where safety becomes very, very important. Now, let us say I put this device on an actual vehicle. Then I start observing a lot of things. There are certain things which actually happen in the real field, which I have not captured in my lab, because I cannot capture everything in my lab or in my simulation also. And this is where and my ML has to continuously learn, update itself, and actually take decisions, right? Because it's a decision-making system that I'm trying to get into. And therefore, there we get into the concept called uncertainty quantification. And this is a huge field of activity across the globe. Uncertainty quantification is a big, big activity. How do I quantify uncertainty? Uncertainty is going to be there. It is not that I can avoid uncertainty, because, life is random, right? We don't know what's going to happen next second. It's as random as that. Same thing with that vehicle or the system. It may be functioning extremely well, but suddenly like this, if you have a flight and your vehicle is moving inside, and still you're still relying on this to give you information. So it has to work. At that time, those things are not captured in your lab. And it's impossible to capture everything in the lab setup. So how do I capture that answer? So suddenly it will flare up and say, I'm seeing something which I have not seen before. So then you have to first qualify that, whether it is really a problem or really not a problem. Is it an outlier in the system? It could be an outlier. Or it may happen only once in its entire lifetime. So I need to first of all identify that. So, and then make the system understand that if it's an outlier, let it give a warning, no problem. At least I know that something has happened. But whether it is so serious that I need to stop everything, things like this. So originally this whole concept of digital twin was meant for basically preventive maintenance, condition monitoring, etc. But now that the system is becoming more and more intelligent, you can, sky is the limit. You can imagine the applications of this for everything, from the fleet management that we are talking about to, everyday life. And medical applications of digital twin is just amazing, because you have these smartwatches, which is collecting a lot of data. But what do I do with the data? It can say that my heart is not beating properly, but does it tell me what do I do with it? Or can it tell me that I'm going to live for 10 more hours? This is the fundamental question that we are trying to answer. So let me use some. Our approach basically is the following. So if you think of conventional product development, it's on the left-hand side. I start with the concept design, I develop a product, test, validate, and this has been happening for the last over 100 years. The second level of this was try to understand what could go wrong, what we call as the fault detection. Lot of work in the early 70s, 80s, quite a few of us were also involved in all this, which comes under a classic problem in engineering, under fatigue, fracture, things like that, where we try to understand under operational loads, is it going to fail, or if it's going to fail, how it is going to fail, etc. But we never answered the question, what happens if it fails? Can it have a certain life after failure, etc. Now today, we want decision support systems, where this device should be not only be able to take its own decisions, but provide information for decision making. This is very, very critical, because I can take the data from here and feed it to new product development and make my next product even better than what I have right now. And therefore, a lot of information from this, we want it to be fed into new product development as well. So where we are today is that we are moving from the conventional approach, a lot of genetic algorithms, neural networks, so much, quite a few of us were involved in the late 80s, 90s, etc. So the technology or the foundation is there. Then we started working on classification models. This was all 90s and 2000s. Today we want to go one step away, where we want to work on physical models, bring in probability, statistics, and reliability into this. And physics-based analytics is something that we talk today. Of course, we have gone one step beyond this. Today we are talking about image-based analytics also, so that the ability for my machine learning algorithm to take a better decision would be even better, because I have more than one data point to take decision, one based on the physics, one based, for example, in some specific cases that we are looking at on the images. Okay. For example, with CMTA, we are working on developing of a smart heat treatment furnace. And that's where we're actually looking at image-based analytics in situ inside a very high temperature chamber, and getting the micrographs of the microstructure and relating that with phase series models available in material science. Okay. Some of the things that we are trying to attempt are some of these things which have not been done before. Okay. So there are a lot of applications of and the manufacturing industry really needs a lot of support on some of these things. So today, the whole idea is to develop or generate the advisory. Okay? We need the system to be intelligent enough, capable enough to provide an advisory. So for an ordinary operator at let's say the factory shop floor, it should give him information enough about the state of the system, whether something can go wrong or if something can go. That is at his level. One level down, it should give information of exactly what went wrong if something went wrong, so that I can make those corrections in the new product development. And then, of course, the third level is by itself, it should be able to correct and move forward. This is the sort of technology that we are looking in, and therefore it starts with data acquisition, data manipulation, state detection, health monitoring, prognostics, and then of course provide the advisory. This is really what the industry, every industry is looking at it. It's not just automotive, aerospace, medical, health industry is really looking at a lot of this. In fact, if you come to here, you have seen that the autoclave. So now we have developed a digital twin for that autoclave also, which is a sterilization equipment used in the medical industry, and they want to improve the performance of their sterilization equipment. So we are a strategic research partner for Stryker, and we are doing a lot of work with those people, especially on the digital twin side. Again, the knowledge is same. Algorithms more or less are same, but the application of the knowledge is to a different field. So so let's look at these challenges which I spoke about. So if you talk to the conventional AI/ML person from the IT industry, first thing you'll say, I need millions of sets of data points. Honestly, we don't have it. Okay, so I had to tell him that you have to learn to live with me, because I only have so many data points. So that is when the technology on the sparse data analytics, we did quite a bit of work on the last 4 or 5 years, and we have developed our own algorithms also. modified models, but to suit specific applications. And so today we talk about sparse data analytics, physics-based analytics, and decisions to be made by devices on physical responses. This is one of the primary requirements of. So, and as I said, in real engineering, most problems happen inside the system, and data is coming from outside the system. This you start realizing when you develop your first digital twin. Everything is a problem. And nothing against my close German friends, but they question everything. Every single data is questioned, okay? And that's where, you start developing these technologies. So, Roland and we laugh at this, but both of us are like, we have got used to it. So, we are afraid to show data to my German colleague, because I know the first thing he's going to ask is, how did you get it, okay? Or why did you get it? And computation of RUL, which is a very critical component, because not only I need to do the diagnosis in terms of trying to identify what the defect is, in terms of prognosis, I should be able to tell the ordinary operator that this can be used for some more time. The other business models around this, which we have talked to Mercedes also, but different countries have different problems, and therefore some of them have not been implemented. For example, if I integrate a GPS to this, and let us say the brake of my vehicle has a problem, one thing it will tell me is that it has a problem, and it could also tell me what the problem is, and it may ask me to stop, or it can allow me to move forward. But with the GPS, it may be able to say that a mechanic who can support this repair is 30 kilometers from this place. Definitely possible. But in Germany, the issue with trying to identify where the person is a major problem, because nobody wants to know their present location. It has its own implications. So that is one reason that GPS is a very good business model, because I can rent the digital twin at a cost for you, like all our cell phones. So I can charge you some 10 euros per month or something like that, which helps you actually drive safely, nothing else. But associating a GPS in US or Germany is absolutely not possible, because they don't want the personal information to be available to anybody. Okay? So some of the work, this was the original work we started with Siemens. Yeah, please, sir.
When you were talking about digital twin in transportation, there will be a spatial digital twin, right?
Yeah.
Because you have various entities. I'm talking about the independent entities who are having their own ways of working. And then you have the temporal digital twin as well.
Correct.
So how do you handle the dimensionality part?
That's something that we have just started looking at, okay? Because you're absolutely right. Originally, we developed a digital twin for a system. Now what happens is they have to work in integration. And this is exactly where the spatial issue is coming up right now. And also what happens is you're looking at different parameters for different systems, which could be off totally, even in terms of dimensions. For example, temperatures in degrees centigrade is all in, let us say, double digits, in the sense 10 degrees, 20 degrees, 80 degrees, 100 degrees. But if you look at flow, the flow could be even 0.1 liter per minute. We have in fact, we are having some serious problems with our algorithms right now when they are integrating. In fact, this is a problem that we are solving right now. In fact, I don't even have a sensor, which I'm not getting here, for the automotive application, where the flow is 0.1 liter per minute. In fact, if somebody knows somebody who can give me that sensor right now, I'm ready to buy it. If you come to the lab, we'll show you live, sir. Because this is another challenge that I had to include in that slide. You're
so
absolutely.
We are going for a connected vehicles or IoV or whatever you talk about, which will be there maybe 5 to 10 years down the line.
Yeah.
So then what do you perceive is going to be the main challenge, not the challenge today. Challenges are there definitely today, but we are just at the taking off stage. where we don't have the full overview of the challenges and the independent data points.
Correct.
And then it will be on the temporal scale.
Correct.
And then the question is that we have to make a decision within maybe a few milliseconds.
Few milliseconds, yes, you're right.
I mean, day before yesterday or just 3 days ago, we lost Mr. Mystery.
Mystery, correct.
Okay. I'm not going into the fact whether they used the
Yeah.
seat belt or they used at what speed they were driving.
Absolutely.
But the point is that if I'm talking a state like that from safety point of view, what are the challenges you see? I'm not asking for the solution.
No,
I'm just
correct.
asking,
I mean,
in your perception, what are the challenges you see in a situation like where we lost Mr. Mystery?
Exactly. So if you look at it, okay, it's not that some technology is not available right now. So for example, if you drive a brand new car right now in US, for example, be it Toyota, be it Mercedes, be it even the most ordinary car, they have implemented a lot of this technology there. For example, you don't have to call it necessarily as speed breakers. But one thing for sure, what they do is, I'll give you some examples of the technology that they have developed. For example, if you're going on a curb, a lot of people try to just go with the same speed. But I have to reduce the speed, and some braking action has to happen, and then I have to go onto the curb, and then I have to. For example, if you drive a Toyota today in US, you may be driving at 80 miles per hour. But it has enough information, so you know, I mean, it will ask you where are you going from point A to point B, means that it also knows all the, exits that you have to take, etc. So the moment it knows that you're trying to take an exit, it will actually slow you down. Number two, for example, you're trying to speed up and there's a car which is going at a much higher speed or lower speed in front of you, it will automatically apply the brake regardless of, whether you want to apply or not. So there's a lot of control which is provided to the vehicle. So that means there is an operating envelope that has provided. It is like fly-by-wire only for the aircrafts. So my operating envelope is clearly defined, and no matter what, it will operate within that envelope. Had I had the operating envelope, and in our country the problem is, I call it as pattern and chaos. Okay, the thing is that everybody is driving at different speeds, 200 different types of vehicles are around you, and honestly, sometimes we don't care and we start driving at speeds which the car itself is not designed for. Okay, now in that case, if I had this operating envelope defined properly, it would not have allowed them actually to even speed up at that point. If there was a curb, it would have stopped them. Things like that. Okay, so it's not that sort of spatial information, what I call as conglomeration, has not happened. It has happened, but we need to also have associated, what I call infrastructure to make it work. So there are two things: the environment in which I operate and the operating system itself. So I can make this to operate in a certain envelope. But if my environment does not provide the facility for me to operate within that envelope, then I have a serious problem. So there are additional challenges in countries like ours. But if you take typically US, for example, today the entire vehicle is not in your hands. It's actually controlled by many microcomputers. I'm running short of time. Yeah. So I'll do one thing. I've taken some special permission from our Siemens to show.
If I may just add one more question. The thing is, in engineering, biology, everywhere, we follow the reductionism. We take a large problem, break it into small pieces, try to understand that small piece, solve, bingo, fine. But the point is that when we are talking about connected systems, 10, 20 years down the line, we need to do anti-reductionism. So how do you see anti-reductionism?
So in fact, there was one problem that, so in fact, way back in 2003, 2004, me and Roland were working on very specific problem called as automated immune systems. For example, in our body, if something gets into the body, instantaneously it recognizes that there's a foreign element that has come into the system and tries to drive it out. So there's a technology that we were developing at the time called artificial immune systems. So when I have a connected car system, when does the problem happen? And what could be the type of problem that can happen? you have to list that out first. And only once I know, then I will go with the technology to do the diagnosis. That's why this digital twin has two parts, the diagnosis and the prognosis. I should be able to diagnose what the problem is. The moment I know what the problem is, then I should be able to do the prognosis also. So in this whole thing, the diagnosis and prognosis therefore becomes very, very important for decision making. So all the tools that I develop for connected car systems will involve the diagnosis part first to find out if there is a problem. So something happened, so I need to know, ahead of time I need to know this could happen. And that is the sort of the test cases and the scenarios that we need to set up, okay, to understand the diagnosis, because I am making the system understand that this could happen. So the test cases for diagnosis becomes therefore very, very important. So what are my test cases for diagnosis? And then if I have the problem, how do I do the prognosis part? So I'll just quickly skip these slides. So this is actually our lab facility for the digital twin for the motor. This was all set up for Siemens, and ultimately we are able to even give them the RUL information. So today Siemens don't sell their motors, they actually sell the number of hours with a lot of confidence. This was the original digital twin that we developed, which was basically wired digital twin. Today we have the wireless version connected to the cloud, everything that you can think of. So we got away with the wireless digital twin a couple of years back. And we also developed digital twin for machine spindles. This is for Mercedes transmission. Yeah, so if you come to the lab, we can show this live. Right now this test rig is up and running, and we are actually doing exactly what you talked about. And associated with that problem is this problem, wherein they have a lubricant system which runs inside the transmission, and a lot of complexities in that. Even after 100 years of the technology, they still think that we can make a lot of improvement on this one. So these are all well within our lab. Please come and have a look at it. And some of the other digital twin activities that we are working on for various other customers. One video I will show you in the interest of time. It is just 2 minutes, because you will get a feel for how the actual digital twin is developed. So this is directly from Siemens, and this is where we started about 5 years back, and you will see where we ended up. Is actually from Siemens, who comes to our lab, and a lot of testing he does it himself. So these are all the live data from the digital twin itself. So there's no other external device that's there except that, and it does everything from provides information on the time domain, frequency domain, everything is embedded inside that, and we have used R for coding, the whole thing. Originally we used Python, and now we have shifted to R, because R libraries are much better than the Python libraries. And then of course we did a lot of validation between.
Nice to hear that.
Yeah. So this was the original digital twin, which was all completely wired. And today what you see on the top there in white, I can go back and show you. It's a very small device whose form factor is just 40 by 10, and it can do everything. What you see sitting on the top of the.
So this is basically, so then you're talking about this digital twin. It's for new product development. So
the data from this can be used for new product development.
okay, but you so
this is mainly meant for preventive and condition monitoring of.
So this setup will be, means you have lab, means are you expecting that somebody will send you the actual physical component?
We are going to actually put it on the customer's physical component only. Yeah. For example, in Siemens, initially we put it on, they have a motor manufacturing facility in Mumbai. So literally we took the digital twin and put it on that system first. Now it is going to go on all their motors.
And here decision making is done by human being?
No, by the digital twin.
No, digital twin is going to generate the data.
No, and
But I'm talking about the decision making.
the decision making also, I'll show you. There is one last picture that you will see how the decision is made. It's just coming to the end, so I will show you. A lot of GUI has to be developed for the to help the decision making, and we will show you basic GUI that we have developed at different levels. All these are all decision making tools. It will keep on telling you whether you are going to the red line, yellow line, green line, based on even you have integrated the ISO standards for motors into this, so that real time you know in what direction this is going, whether there is a problem, no problem. Every decision is taken on that peak. So this is the first level of decision making. Here it gives information about vibration, temperature, current, and the remaining useful life based on this information. It also gives him a warning saying, okay, you are going to come towards yellow, for example.
Thank you. I think Roland is waiting.
I'll just leave it here. So,
Whenever the discussion is going on and flowing, we should not just interrupt it.
but I just wanted to give you a broad brush perspective of all the challenges, basically, and to our best knowledge, this is the first ever digital twin, actual physical digital twin that has been developed. Okay, we honestly don't know any other one that has been developed, and we were given a lot of credit by the CTO of Siemens for this development, and we really thank Siemens for supporting us completely, over 5 years for this project. Yeah.
Sorry, sir, I understand. So the left three plots are
The state of the machine.
of the sensor data.
Yeah,
The right RUL is what is the output from your model.
correct.
So you say RUL vibration, so you have an RUL bearing temperature and RUL housing temperature as well as outputs?
Yes, this is just a representative plot. And like as I was trying to suggest, these are all temporal data if you look at. Spatial data, combining them also we have one.
So will you intend to combine all into a single metric of RUL, or is it?
Yes. That's the whole idea. Decisions can be taken on the individual data, but really what is happening is everything together. For example, when the vibration increases, my temperature increases, current also increases. Okay? Yeah.
One question from me. This entire concept of this digital twin, what I understand is one of the parameters of probably the highest importance is the data itself. So how to ensure that the data that is getting filled into the system is robust, is not corrupted, because as things becomes much more connected, right?
Yeah.
It can
So,
be compromised.
exactly, that's the reason why we have the test facility and also the simulation facility. We actually integrate the two. And 99% of the time, the simulation may not marry 100% with the test. That is where we work on semi-empirical formulations. These are basically transfer functions which relate a certain input, a certain output to its dependent parameters. For example, here, vibration, temperature, current are dependent parameters. My output could be RUL, for example. Okay. Now, the whole problem here is, number one, those three data has to be correct, and they also will be correct within a range of its parameters. Like it will have an upper control limit, lower control limit, because it's all based on statistics. Therefore, my control limits become important. Now, therefore, first of all, I have to sanitize that data. Therefore, data coming from the sensor is what it is. Nothing much I can do, because the physical system is behaving like that. But the data coming from the simulation has to match with, and my simulation is an approximated model. I approximate my material properties, my boundary conditions, my loading, etc., etc. So we actually bridge that gap, and we develop a combination or a transfer function which is a combination of this plus that. For that, we have developed a lot of predictor-corrector methods, wherein I predict, correct, and ultimately develop that for this system.
So you can filter out the spurious.
Yes. And there's a lot of noise in the system when you talk about vibration. The noise has to be filtered. So there are a lot of levels of details, when you develop it. So you are absolutely right. It's not a simple one-step solution. In fact, we have almost worked 18 hours a day to get here for last about 5.5 years. And for almost 1 hour, 1 year and 3 months, Punesh, I brought him for that reason. He was running the lab. Of course, we ran it in closed loop so that no physical person can be there. But we ran it for what, 1 year, 3 months, because defect data is not generally available to you. Okay, no company shares defect data with you. And that is also one. So we have to create the test rig, actually get or produce the defect data. Otherwise, my RUL cannot be computed. Okay, and it's because it's based on the reliability model. So yes, you are right. There's a lot of details. I didn't.
The question I have is that when you are on the digital twin, you should be able to generate synthetic data. Synthetic noise.
Yeah, once it's ready, yes. Not before.
Why not before? Because it is coming through the sensors. Okay, when I simulate that, I should be able to add noise. I should be able to also synthetically generate data. Today, computers are painting different.
You are absolutely right. No, I think I made this comment in the very beginning. I said that we do, therefore, the numerical simulations and create all possible test cases in the numerical simulation. I may not be able to create a physical system for all the test cases. And you are absolutely right. A lot of such data is generated from simulation only. And if you see, there are certain companies who claim they have digital twin. If you talk to them, they will immediately say, no, I will run this finite element model in the cloud. But we said we are not going to go through that route. Huge models, if I have to run each time, it makes no sense to me. Rather than that, if I have the response data which are collated in a particular way or classified in a particular way, I don't have to run the simulation. I can take the in situ data and start comparing with that and then say that with this level of probability, this is the state of the system. That is the technology that we used and developed. We said we'll avoid doing that. We'll do it once, but that is done, data is stored, and then I will only take the in situ data, compare and take a decision. So like that, lot of optimization in terms of saving time, money, even doing simulations, etc. we have taken care of in these things. I have not spelled out all the details, I just give you an overview. But you are right, all these questions have been asked and many have been answered.
Professor Suresh, thank you very much. I would suggest maybe we can move over to tea and coffee and then continue discussion. I hate to cut it short now, but I have to look a little bit at the timing because then the next part will be our panel discussion. If this is okay, we can break out to tea and coffee, continue discussion over tea and coffee. And Professor Suresh, thank you very much for that overview of digital twins. And also the remarkable work you and your team are doing here right in Bangalore on digital twins to advance this thing. Maybe you can just ask a question so that everybody knows what,
No, I just wanted to know that since you have this working setup now, and there's a lot of inputs going from this investment decisions and prediction, do you also observe any kind of false positive response or should be close to the accuracy?
No, that is exactly where the ML has to be tuned. That's what I call as outliers. Especially you will see that when you put this on an actual physical system. For example, digital transmission, if I put it on an actual transmission, that is when all these problems will start coming. Then I should be able to classify them as good, bad, or I can ignore, not ignore. And if it's a serious problem, that has to be, I have to make my machine learning understand that next time such a thing happens, it has to identify that as a defect and let me know. Yes, in fact, I can give you a lot of examples, including in this one, where once we put it in that Siemens center in Mumbai, and 3 days everything was fine. It also showed some defects. They were all very happy. But on the 4th day, suddenly we saw some outliers in this thing. So then suddenly we didn't know. So you come back to the drawing board and see what's happening. Then we suddenly realized that it was a problem with the voltage in our country. The three-phase voltage is not necessarily 220, 220, 220. Some of it was 210, some of it was 240, some of it was 230. So we actually built a voltage stabilizer where I can manually change the voltage so that those experiments can be conducted and the data can be fed into my ML so that next time it happens, it knows it is because of the voltage fluctuation. And so those things you would not have even imagined when you have the testing in the lab.
So this is one of the key challenges. That
Yes,
if you
yes.
start getting too many false positives, then whole systems.
Exactly. And especially if, absolutely right. Yeah.
Different kind of issues.
Yes,
solving the equation.
yes, you're absolutely right.
True. The tea and coffee will be served outside.
Sure.
I would like the Infineon team just to raise your hand, please, because I have to give a special thank you to the team from Infineon. They are sponsoring today's workshop.
Excellent.
Event. So lunch, coffee, tea, everything is sponsored. So thank you so much. We can continue the discussion outside. I would suggest we will extend the networking break by 15 minutes, so we reconvene at 10:45 here.
Sure.
For then the panel discussion. And please remember, if you have a topic which you would like to be discussed, write it up here. Then we will make the groups after our networking session and the panel discussion, and then break out into the different rooms for individual work group discussions. So thank you.
Thank you so very much. I hope it was interesting and useful because new technologies, new challenges, so we have to come together.
Ladies and gentlemen, dear delegates, now we have our panel discussion, and I especially would like to welcome also the media who has joined us now. So we not only take a video recording, but also we have the media here that will report about our event. And so a warm welcome to them. So looking a little bit at the time, I just take a few minutes to introduce our special interest group Automotive, because you have heard that and saw that also in the beginning of the workshop. This interest group is actually a cluster of professors who have an interest or work on subjects that would be relevant for the automotive space. It's currently managed by me and my dear colleague Sujit, and we have those professors here who actually comprise this group, each one presenting a different domain. I just will pick out a few here. We have Web3, semantic modeling is one domain. That's Professor Srinath, who is also our dean. We have Professor Sajid with us, who is into systems engineering, control systems, collaborating quite a bit with the engineering world and the automotive world. He's over there. Welcome, Professor Sajid. We have Professor Vivek, who is with us here, who is also handling the special interest group on cybersecurity. His areas like crypto engineering and side channel attacks are, of course, very relevant also for the domain of automotive cybersecurity. But we also have representatives from different other domains. Professor Milind Gande is with us there. He is also handling the Minrose Center, and he comes from the industry also with deep knowledge in the automotive domain. So all of that actually with different fields from radar to software engineering, systems engineering, control systems, and Web3. This together forms a group that actually contributes to these activities in the automotive domain. And today is our first workshop where we as a group also come together for this industry-academia interaction. Professor Sujit, of course, from the software engineering domain will join us now also on the panel. And with that, I would like to ask the panelists to come forward. We have Professor Sujit to join us on the panel. We have Dr. Soya Munsunuri to join us on the panel from Infineon. And we have Dr. Pralat from MathWorks, who will be the third panelist to come to the panel, please. Today's motto of the workshop, keep it interactive, industry meets academia. We don't want to go into monologues, but into an interaction with everybody in this discussion. So let me briefly introduce our panelists. I would like to start with my colleague, Professor Sujit, and he was so kind not to write a very long, CV on this, but I give you some pointers of what he has done. He is a PhD from the Department of Computer Science and Automation from the Indian Institute of Science here in Bangalore. Prior to that, he has a master's from the University of Roorkee, now IIT Roorkee, and he has an degree in electrical engineering from Nagpur University. He is interested, and his areas of research are centered around software engineering, formal methods, programming languages, education technology, and software testing. Sujit has nearly 8 years of experience in the industry with companies like Tata Consulting Services, Philips, and General Motors, both in research and software development. And as I understand, also some of your former colleagues from General Motors are here today. Prior to joining IIITB, Sujit was with JetI, an educational startup. His interests are, of course, programming, as one should have an interest in that if one is doing software engineering, tech blogging, and I know myself he also has a hobby and a very keen interest into cartoons, drawing, and so welcome Sujit to our panel here, and maybe you can draw the final cartoon of the whole conference workshop that summarizes in a pictorial way what we have been discussing. Welcome, Sujit.
Thank you so much.
Then to his side, we have Dr. Pralat from MathWorks. I understand you also interacted formally to the industry interaction you have. Let me just briefly talk about some of the pointers he has given me about his career. He is currently an engineering manager at MathWorks in India, and I think MathWorks needs no introduction. It's a very well-known company where he is leading a team working on verification and validation tools for Simulink, Stateflow, MATLAB, and C. Actually, if I look back to my career when I started first, early in the 90s to work with Simulink and MATLAB tools, of course. This includes Simulink Design Verifier, Simulink Coverage, Simulink Check, Simulink Test, and Body Space. He has earlier worked as a researcher at TRWDC in Pune and General Motors India Science Lab. Pralat primarily focuses on applying formal methods, based techniques to address software engineering problems. Dr. Pralat,
thank you.
I welcome you to our panel. And to his side, we have Dr. Surya Munsoluri. I hope I pronounced it correctly. Please bear with me with my German accent. He is also a very distinguished engineer. He has a PhD in electrical engineering from the University of Urbana-Champaign in Illinois, USA. About 20 years of experience in various industry groups, including Intel and Apple. And he is now currently a post-silicon architect for the Oryx 3G microcontroller at Infineon. So, Dr. Surya Munsoluri, welcome to our panel. Yeah, so we have a lot of experience here in, obviously, software engineering, methods of software engineering, with a relationship also to the automotive space. And I would like to start our discussion with one question that, is kind of underlying the whole activities here when we talk about automotive software. And we know that automotive software tends to become more and more. It is now nearly approaching, several 100 million lines of code in a car. Some predict it to be 1 billion lines of code in a car. Not only in the car itself, but of course you also need to think about software running in the cloud when we have a connected car architecture. And some predict it to be about 30% of the complete value add of the car. So this is a huge amount, but this also means there's a huge complexity. So my question here is really, how do we deal with this complexity of automotive software? What are the methods we have? What are the ways we have to handle and can handle this complexity? And I would like to just open up it now before directing to who of the panelists would like to kind of give his thought on this. How do we handle the complexity of automotive software?
So, thanks a lot for having me on this panel, Professor Roland. At least with respect to the goal or the problem statement that we were given, I would like to add one more S to this, which is the system view, right? System, then software, and then sustainability. And the main, I think, as you listed out the problem statement here, I think the system perspective is the most important aspect here. I think especially coming from where my functional role is with respect to automotive microcontrollers, we have to always recognize it's a real-time system. And we need to understand the system perspective also from control aspect, to realize that it is not a linear time invariant system. It is a non-linear time variant system, okay, which we try to reduce it into a more manageable complexity. So that's one aspect. The other thing that obviously Infineon's strength is on safety, the functional safety aspect, so the safe and secure systems. That means that there is a level of fault tolerance built into both hardware and software. So that would be my opening statement, to manage this complexity, to bring that perspective.
Yeah, thank you. Thank you, Dr. Surya.
Once again, yeah, thanks, Professor Roland, for inviting us. Thanks, Sujit, for inviting me to this conference. Really humbled by the illustrious guests here. And it was we had a fantastic speech, keynote speech. Thank you very much for that. When you ask me, what is it, how do we manage complexity? Complexity is not new to humans. We have managed complexity. Our political systems are complex, we manage it. Our city systems are complex, we mostly manage it. In Bangalore at least. At the moment I can only say mostly. And historically, the way we have always managed complexity is through modeling. We take a complex system and come up with what we think is a manageable model, which we can manage computationally. We take that model, we simulate it. We try to see how it matches up with reality, and we adjust. Now, this, I think Surya also, you mentioned that it is, we have got different mathematical techniques. So you have got time invariant systems, linear time model, non-linear models, and there are tools for many of them. And I would say that as a human race, we have spent thousands of years in building some of the tools for it. Most of them happen to be mathematical, but those are not the only kinds of tools. We have philosophical tools. Right? When I looked at the topic, we had sustainability. And in my mind, sustainability is the ultimate goal. It is how we can take what we are doing and keep doing it forever, sustain it forever. That's a vision, and everything else is building towards that vision. And sustainability has 3 pillars, right? So you've got economic sustainability, environmental, social, and the things that we are talking about here is pretty much hitting on all parts of it. Now, how do we tackle this complexity? Once again, I would say that it is through models. We have got more. Our tools may seem inadequate right now, but that's what we have. And we have a history of taking inadequate tools, trying them out, testing them out, and improving them. And that's, and also currently I am working at a company where we are encouraging model-based design, which is we are trying to build tools which try to simplify the complexity, simplify it, model it, simulate it, and adjust. And the modeling formalisms, tools, they change over time. So we started with simple linear equations, we went to nonlinear equations, we have got a graphical language, now we have got machine learning.
my knowledge of machine learning is not great, but it is also a model. It's a different kind of model from a normal mathematical model, but it's a model. And it allows you to simulate, it allows you to study it, it allows you to make projections, make predictions, which can be tested. So these are the things that I feel are the core for our approach to managing the upcoming complexity. It's not new. It is just we are now seeing it and we are saying, hey, this is complex, we need to solve this problem, and how do we do better at every step of the way. Thank you. Okay, we got this.
Okay, so I have to maybe bring in the third angle to this. So one is systems, one is modeling. This is better, isn't it? So I will put on the academic's hat, and that too an academician who is teaching in an Indian university. So I think, while we have complex systems to manage, understand, analyze, control, and we have devices and tools to do that, I think we need people to handle all these things. So I come from that side. I would say that one of the very important ways to handle this complexity is to prepare a workforce which is able to handle all these tools, techniques that we are talking about. So I think all my perspectives that I will be sharing in the rest of this panel will be coming from that angle. Okay, so I'll reserve the details for further questions. So this is my opening remark. So we have to prepare our students to be able to deal with the systems. And currently, we, my one-line verdict would be we are not doing a very good job there. A lot needs to be done there.
Okay. Yeah, thank you very much for that input. Maybe, Sujit, I can, kind of continue there what you said from this academics perspective. What do you think are some of the things that an automotive software engineer that would pass out of an institute like IIITB or similar institutes need to know? What are the basics they need to know apart from some theory and some programming skills?
Okay, Roland, thanks for that question. So, so my one observation is, so I come from an electrical background, electrical engineering background, and I kind of migrated to core computer science over the years. And I have always felt that my mixed background has really been very helpful in my being able to, understand things. While I feel that, the way computer science education or information technology education is going, it is becoming more and more specialized. Some unsaid assumptions are already there in the heads of both the pedagogues as well as our learners. For example, whenever we are talking about software engineering, I get a feeling that our students already have a preset notion that we are probably talking about something like an e-commerce website or a banking application, and and they are already prepared to overtake us. So in my software engineering course, they already seem to know much more than I do about how to deal with these kind of developments. Whereas whenever I try to turn them towards some of these other kind of systems, computing systems, which are hybrid in nature, have physical elements in them, they start fidgeting in their chairs because they know nothing of electrical engineering, nothing of mechanical engineering, least of all about physics, chemistry, etc. So I feel one of the things that we probably need to do is to prepare our students with this kind of hybrid multidisciplinary knowledge. I know there is too much to teach, but I am of the opinion that we should forget about teaching too much, let them pick up what they can, but expose them to this multidisciplinary nature of knowledge that is absolutely essential if you really want to do a good job in an industry sector like automotive, okay, they have to work closely with electrical engineers, mechanical engineers, and many other disciplines of scholarly studies. That's one thing. I have some more points, but they are more focused towards computer science. So I think that, from my brief exposure to how systems are developed in automotive OEMs and others, what I have felt is, they use a lot of model-driven engineering approaches, which our computer science graduates unfortunately are not even literate about. Right? So Simulink is so big in industry. Almost all industry, automotive OEMs, aerospace people are using it, LabVIEW, etc., which is a model-driven approach. And underneath it, I see a very strong undercurrent of, for example, functional programming. I think those of you who come from traditional computer science background would probably know about and love functional programming. Whereas, let me tell you, our current generation youngsters, they, at least in India, hardly know anything about functional programming. I feel that's a big lacuna, and that stops them from being prepared for this kind of things. The other thing is, again, coming from what Prahalad said, just to reaffirm what he said. So I think, things like formal logic, formal verification, I think our students are not initiated about good old basic computer science like theory of computation. They take it as a subject that they have to somehow clear. They really do not understand that that is so core to most of the very cutting edge stuff that is happening in the industry. Precisely because we as educators are probably failing to expose them to that sector of development. So we have to do something about that. Let me preserve my other points for later questions. Thank you.
Yeah, thank you very much, Sujit. You see, there's a lot of agreement from the audience.
Question was on the same thing. Basically, how, because every software engineer coming to industry is thinking about only coding. He wants to become coder, but not a designer. So as an academicians or in the colleges, basically the educational institutes are not focusing on the design, but their focus is teach the language and mug up the syntaxes basically, and use those syntaxes. But if you have touched that point, basically no physics, no chemistry, as well as no engineering background. And then the model-based development is happening, which is further killing the things. Okay, I know MATLAB. How the system will work, that I don't know. I will bring some blocks here, connect, and there should be somebody who knows about these things. So how we can improve on the quality of engineers coming out of college from the design aspect, basically. Otherwise, coders, I am getting anybody who can do coding in C or in MATLAB modeling, basically. So how to improve that, basically, from complexity point of view? If the engineer, the coder knows about the design, then the complex system also becomes very simple for everybody to understand.
Okay, so I will probably not try to answer your question because I myself have that question. In fact, I would like to relay that question to the other panelists.
Okay, do you want to take a step?
It's a smart move by the professor. A very, very smart move. But I echo to what is being said. I think it's not just the students, by the way, and this is what I was discussing in the hallway. It's about mindset. I think, like what was mentioned in the keynote, we should first think and feel like engineers. Forget about the domains. We get siloed into mechanical and all these, esoteric terminology. And I don't know, it's a systemic view. I'm taking a systemic view is that it's the way all these, the entrance examinations and all these things, how people always treat like, okay, if I'm the top ranker, I would normally choose CS or E or something like that. So there's a particular gradation built in, and it's built in from the start by the time they are 17 or 18 years old. But even when they enter industry, I see a lot of challenge in reorienting the mindset. Any problem we take, there is, like was pointed out, sir is applying problems from healthcare industry and reusing those models into a completely different domain. It's a very hard thing to do. And without that open mindset, first thinking like, engineers, and even before that, like the basic science students, it's very hard. It's very, very hard. I think that's one way. And unless we open that up, it's also individually, that's what I tell myself as well. Unless we open up that universe of potentialities, it's very hard to manage the complexity, right? I mean, where do you get the inspiration to solve this problem, ultimately? So, for coding or for design or for any job that you take that's going to come up in the next 15, 20 years, not only in automotive, I think it's a mindset, and that's the way that has to be shown. And if I look at the people who are, starting up companies and so on, and a lot of them are multidisciplinary now. So how do you, talk to the other people in the same language? I mean, if you get siloed into just doing syntactical code, right? So back to Prahlad.
Okay.
Can I add one point? A couple of days ago, I received in WhatsApp, which I don't trust or rely. It's a beautiful thing, which says that Bangalore now is a city in India where there are software engineers who take 2 to 5 years to reach their office to deliver goods in 10 minutes to their home. That's the mindset. If you look at the software industry, everybody wants to be either in Uber or Ola or some of those groceries, and that's what it is. The campus just opposite to us, few 100,000 coders. So we need to start innovation in India. The moment we start innovation in India, there will be pressure on everybody to solve problems, not to do a quick fix. Sorry for saying that, but that's my personal feeling. I was in teaching, I was in industry, and that's my experience. We need to educate, graduate our students to solve problems.
Just to add to what he said, just nailed it correctly. Solving problems also means solving problems, complex problems, and not doing for the sake of getting an internship or a job. Because I see with a lot of students nowadays, when I evaluate them from one of the best institutes in the country, I ask them why you have done this project, what it has to do with your academics. And he says that this helps me to get a internship.
Yeah, I think on the last point.
One more point if I can add. The hiring pattern in the companies also has to change. The thing is, everybody asks a question. How many years of experience do you have? It doesn't make any sense to me. To me, what is important is that how many years of knowledge you have. I don't care. If you sit on a seat for 20 years and like hatching, you hatch the eggs, you have 20 years of experience. Who cares? How many years of knowledge you have? We never ask that question. Is it 1 into 20 or 20 into 1? We don't ask that question. HR has been trained to ask the question, how many years, and based upon that multiply with some factor, that is going to be your cost to the company. We need to change that question.
Exactly. I think on the point that was raised, right? I mean, one thing we should do, and which is also part of the agenda, is we should get industry and the universities closer, the more cooperation. Basically, bring in the problem statements at least that we face in the industry. That's what I think, so that we start motivating the students to take up that, as at the bachelor's level in the final year or the master's, and that's, I think, the critical trigger for them to see what's going on. I mean, to open up and say, hey, there are these problems that coming directly as a problem statements from the industry. So maybe that will motivate them to look beyond just, like being an app developer or something like that. So that this is one solution. I mean, one way. Once that proceeds, then we can also think about technology transfer and the next level of topics, but that's where we can start, I think.
Right.
I think the problem starts much earlier in anybody's life. Like when you take a kid, for example, while he's growing up, the passion sort of dies down, and it's fed into that system that you need to give these exams and you need to get your CS degree, and then that's when you're like valued, or you get amazing jobs, or you can go abroad, whatever it is. So the entire mindset is very streamlined at a very basic age. If you take universities abroad, for example, if you ask a student who is doing computer science there, he's not going to tell you that, I'm doing computer science because my parents asked me. He is very passionate about it. But I think somewhere that passion lacking is where the incompetence kicks in, where there is no creativity in the solution or in your way of studying itself.
Okay, so there are a few questions addressed here. So there are some very interesting stuff that Sujit talked about, and there are some very interesting points you brought about what our culture is, and also some things you told about what our current education system is. Let me start with the last. So in the current education system, I have 2 kids who are teenagers, and I can say for a fact that times are changing. It maybe have been the fact that we did some of those things because we were pressured to do, but I know my son and my daughter are not going to do what society is asking them to do. They seem to have extremely strong opinions, and believe me, I have tried. Okay? They have strong opinions, and so I am actually optimistic. I'm very optimistic. I can see the seeds of independent thought, independent reasoning in the kids of today. And I'm pretty sure many of you would have used the term, oh my God, these millennials, how are they? Well, I think that's positive. They are thinking for themselves. They are making their own decisions. They may be basing some of the decisions on WhatsApp, but that's a technology, and that will change. Some of that will change because I feel that they are able to reason, okay? And which brings me to what I think is core in an educational institute. In my opinion, the thing that should be taught in educational institute is how to reason. Now it is very easy to say how to reason, how to have critical thought, how to think about problems, how to approach problems, different techniques for breaking up the problems. I don't remember having studied it. I don't remember having studied the philosophies of thought, the Socratic method of thinking, or sir here used this word of, reductionism. That's a philosophy of thinking. It had its time, it had its place. Even today it has its place. It cannot be applied everywhere. How many of our students know about thought, about thinking? And only from that we'll get to design. Now, I do not see many courses in school. These are things that should be introduced at the very early education level, at least to some extent. Okay, you've got these ideas. And as they grow, they will develop more of the ideas. Now, in terms of things like coding, my opinion is that we are at a phase at this point where things are changing rapidly. Technology is changing, code is changing. I am personally, when I was in university, I spent a lot of time learning of programming languages. Luckily, to some extent, I had the opportunity to go down the less treaded path, and I got really interested in functional programming languages at that time. And I had my situation was different from any other people that I've seen. So I had the opportunity and I was encouraged to think for myself at that time. I consider myself lucky for that. But now, when I am looking at myself, when I am evaluating people who are interviewing people, I do see that in many cases we ask for, hey, how much experience do you have in C++? Right? That's a question we ask. And when I am reflecting about it, why do we ask that? We ask that because we are in an industry which we are trying to make progress. We are trying to optimize, and that optimization is local. And I do recognize that it may not serve the broader purpose, but it is very important for each local group to succeed as well. However, so just 1 second, sir. Some of the things that we end up doing is actually different. So at least from a personal perspective, right? So let me share a little bit of how we are taking in freshers. When we take in freshers, we, at least in MathWorks, we enroll them into a EDG program. Now that EDG program, it depends on, some people are there for 3 months, for 6 months, 1 year, whatever, it's up to them. And in that program, they have an option for, they get trained in, definitely the company culture, the way of thinking, how we want to think, how we want them to take ownership, how we want them to design. Exactly what you're saying. Not code, but design. Think about the customer, think about what the problem is, base the problem, explain the problem, and explore alternatives, and justify why you think one alternative is better. We do let them develop some of those skills, and along that time, they also have the opportunity to work with different engineering teams, or the pre-sales teams or the sales teams, whatever. They have the option to explore, and we encourage them to take the decision of where they want to go. So there is some sort of an internal, almost an internal university where we take in freshers and we do that. And to some extent, we are able to do that, and this is something that is getting built into the culture of the organization. Almost anybody who is fresh comes in through this EDG program. So this is something that we are doing. My belief is that even if we make all of these changes which you are talking about, we are saying that, okay, academia should be teaching about various skills. Some of these programs would still benefit because that's a way of thinking. We are saying, hey, how do we, it takes time. I mean, human beings are human beings. We are not machines. It takes time for us to change our thought process from being a student to being a contributor. It takes some time. And people need the ability to change, and they will need to change at their own pace. And frankly, at the EDG program, we have people who are from all streams of engineering.
Can I add one point?
Please, go ahead, sir.
So what I was saying is that we as an employer or senior need to challenge our staff, our students.
Yes.
Because everybody, we talked about coding, everybody's first program is a copy-paste, which is Hello World. No exception. First program in everybody's life, doesn't matter what language it is, whether it is Python, whether it is C, C++, Java, first program is a copy-paste. Hello World. The question is, we need to challenge them to graduate from copy-paste to solving problem, which we never do. So we have a responsibility to challenge. But anyway, coming back to the point of the discussion complex system, I have a question to both of you. Could you, for the general knowledge, is that how would you like to use formal systems in complex systems like automotive?
Sure.
Can I just add, learning has to be continuous.
Yeah.
This is something that we also see as a lacuna even in the industry. Because you're used to the traditional mode of thinking and you don't want to break the ice and try something new. And so if you don't have challenging projects even within your own industry, then there's a problem.
We need
to be very honest, in India we have become dealers.
Sorry, I'm sorry.
Become dealers. I buy it, I sell it to you, I make my money. we don't spend money on.
Yeah, all the companies are service company. Anyway, let's come back to.
So what I'm
the
trying to
topic.
say is that if learning is not continuous, definitely people like us of our age would not have even thought about a digital pen.
So formal methods in, excuse me, I've got one point.
There are many points here.
So many automobile industries, the high-end electronics vehicles are being released, right? Now, of course, I think I am the oldest person sitting here, most probably in this group.
Good.
May not, yeah. Okay. So I have seen a scooter being a Vespa scooter when we used to start. If it doesn't start, we used to incline, hold it inclined and kick start it and start it. And somehow it used to get started and I used to start my journey. Today, gearless scooters are there. If it doesn't start, will you be able to start? High-end electronics, fantastic. But my problem in India exists. Okay, let us come to automobile car, high-end car. Let us go. Earlier, I used to push my car, put it in the first gear, run it. Yes, battery, even if it is drained out, I will start the vehicle, I will reach my destiny. No problem. Whereas today, you have to press the clutch first to start your engine. But there is a safety, I agree. Children cannot start, suddenly you cannot switch it on, something, for that safety purpose, you will have to press the clutch first, then start your car. Okay, battery suddenly got drained. Now what is next? Wait for the help. I cannot take. So in developing any technology, people are forgetting the basic, facility available. I think these things can be introduced very easily. I do know a little bit of computer, later may not be master of, my main domain is space science, space technology. I am coming from space technology. These are all the problems which creates havoc during emergency operations. For example, I tell you, during Gulf War, Israel was being attacked from all around, from all countries around it. What happened? See, Syria purchased 100 MiG-27 aircraft from Russia. They wanted to attack Israel at that time. All 100 aircraft at that time. Israel got the information. They found how to manage this. He said, Israel is a very small country. 100 aircraft riding means matter of a few hours, Israel will get reduced to dust. Then what is to be done? They started hunting for they went like a caravan on these camels. Right? It is all around it is a desert. All around it is a desert. They went on a camel. They loaded the missile head on camel. Nobody thought of it. They went like a caravan. 100 aircraft came to Syria from Russia, parked in the airport. They were ready, and the date was decided when it was supposed to be attacked. Before that, the caravan went there, fired all the missiles. They thought that some caravan is going 1 or 2 camels. They fired the missile. 100 aircraft gone in 3 seconds, 3 minutes, maybe. See, ultimately, technology, which technology worked? Not high-end technology. Technology of the lowest, what human thought, this brain thought. Next, I would like to give you one more. India and Bangladesh. I think I was in high school on those days. My father was involved in this, so I know a little bit of this. Chinese built bunkers were there in the Bangladesh and India border, where thousands of soldiers can take shelter inside the bunker. And if you see the Google, this is the world's record. 2 lakh soldiers got surrendered, Pakistani soldiers got surrendered. I think that is the Guinness record India did.
how it is, and Indians, aircraft when bombarded, bomb is jumping up near about 20 meters above the ground and there it is exploding. Nothing could be done. At last what technology came into for the help? They drilled a hole, inclined hole to the bunker, another hole vertically for the water. They filled the water to the bunkers. That field commander whose brain worked, cheapest technology. They took two earth drilling machines, one for the hole for the water, one for the pumping in.
Can we come back
Something like 1.2 lakhs soldiers came out lifting their hands and all ammunition were gone inside the bunker. I want to know why developing, going for a very highest technology, the lowest facility what we are supposed to get should not be lost. Now, I have seen many in Bangalore-Mysore highway, many people, a car broken down, asking for one mechanic to come and start the car because battery is gone. See?
So I guess we have seen now different aspects of that, and it's good because we already have a lively discussion, panel and audience, but I still would like to come back to a little bit the flow of the panel discussion. So we will keep these questions that were raised and discussion points in mind. You just have one more, and then I would like to, kind of go back to the panel interaction, and we keep those questions for the last part of our panel.
So I want to come back to the topic we started with, and the challenges related to again the automotive world. And I have two questions. One related to the design phase of this domain, another in the sustainability. So the first one related to design, either Dr. Prahlad and Professor Joseph can comment. So you already commented that to address this new ever-growing challenges of the complexities and all, we are coming with all these modelings and algorithms to make the life easier, or at least handles this complexity part. But then it has an orthogonal challenges that whatever we do with all these modelings and algorithms, it has to be 100% safe and secure. And this prevents you to do this whatever you want to do, because it's not a POC. You cannot stay with a POC. You put systems into a product and that product becomes a life-threatening product. It has to be 100% accurate. So if my model or my algorithm is 99% accurate, then I'm gone because we have a liability here. So how do we address such orthogonal challenges during the design? Another new question is on the sustainability. That let's say I design systems today with all these the methodologies and toolings and all this ecosystem. And 20 years later, how do I sustain this ecosystem to reconstruct my environment? Because whatever I design today has to be active and alive to 20 years later into the system. Now, whatever decisions we take today in terms of the tooling, in terms of methodology, is certainly going to be obsolete. We may not have support from the vendors, on the tool providers or the engineers who develop it. So how do we handle this sustainability on the ecosystem part? And then with these challenges on the design part where we have the orthogonal requirements.
Oh, Prahlad, you are okay.
Okay. Oh my goodness. Okay. Okay. So the first question was, we need very strong guarantees for the modern systems that we are building, and how do we achieve it? That was the first question. And the second question is, how do we incorporate sustainability into our designs? Because we know that we are taking actions today which is borrowing from our future. Right? So let me first talk about the first one.
You have formal methods in that as well?
Yeah, okay. So formal methods in the first part is what you're saying. Either. Okay. Okay, sure.
Formal method will answer this question anyway.
Okay. So in terms of 100% safe and secure, our systems are fairly complex. Once again, I would like to challenge anyone to tell me whether they are 100% confident of anything, even a Hello World program, right? When we are saying a Hello World program, actually for us it's a mental construct, but when you are actually executing it, it is executing on hardware in a physical system, and we have come to a stage where the error correction in the physical system is so good that we hardly ever notice it. But it is not 100%. And that comes up when we are talking about, hey, we have to design the chip system for aerospace. Well, we have to harden it against radiation. Who ever thought of radiation on Earth? So the assumptions keep changing. Okay? And the only hope we have is agility to keep changing our models to address our assumptions. So in some sense, I would say that the thought has always been going on in our mind. Machine learning is something new. It's a new technology. But reduced order modeling has been there for ages. Right? Right from, I would say, 500, 600 years. I would say that Newton's laws of motions are a reduced order model. But they have been good enough. But when we figured it out, we changed it. Now, where does machine learning come in? Machine learning, perhaps the difference between reduced order modeling and machine learning is maybe machine learning is slightly more agile in changing. In reduced order modeling, we perhaps have a too high a bar for perfection, for saying, hey, this is the correct answer. Machine learning, perhaps not. So maybe the agility is where it changes, and maybe that is why machine learning, it has always been a puzzle to me. Why is machine learning so successful? Why do people want to apply machine learning for everything? When we already had reduced order modeling, when we had physics modeling, when we had software models, we had everything. Why machine learning? Maybe the reason there is agility. So I would say that instead of aiming to be 100% safe and secure, we should build our systems which are agile, which we can change, we can make more robust. And if you think about it, the current trend towards a connected car, electronic car, all of them are towards it. Why do you want an electronic car? Why do you want a software-driven car? Because you can have OTP updates. Okay? That's the reason. You want it to be agile. You want the system to be able to adapt. If you didn't have a connected car, if you didn't have that, you wouldn't do that. So for example, I would argue for one other thing in terms of the technology, just to answer your question. You're saying high-end technology. I am not sure that I'm thinking in terms of high-end technology because the technology level keeps on changing. Things become commoditized.
So my question was, see, suppose there is in case of any problem,
right.
The automobile.
Oh yeah.
Yeah. If the software can handle all, when the system some power failure something, it should come to the manual mode, complete manual mode, so that people will not face any problem. That can be implemented. That is implementable.
I agree. That's our design.
It is not done.
That's our design. And I totally agree with you. So, sir, 1 second, sir. Let me just reply to him. We do have commoditization of technology, and technology levels keep on changing. And and we have to figure out how to adapt. So I'm not sure if I'm answering your question, but I do agree that we need to have places where human can intervene. Yeah, yes, sir, please.
I mean, it talks a lot about redundancy in design.
Yeah.
Okay, because you cannot have redundancy in all systems because it's too expensive.
That's true.
But where systems are critical, and I know that it is going to be a serious safety issue, redundancy becomes very, very important. So to answer your question, to ensure that I have the other 1 minus probability answered means, there's always a probability that something can go wrong. If something goes wrong, then probability. That's the question that we need to answer. Things will go wrong. Life is highly nonlinear. So things on all systems are nonlinear systems. We just call them linear by approximation of simplification. Okay? But the issue is we build in the redundancy. We assume that things will go wrong. If you assume that things will not go wrong, then I'm actually creating a problem in my design.
Yeah, because the only thing is that redundancy in the hardware is manageable. You can do a redundancy in the hardware. How do we address such redundancy in the software? Because the moment you say that software is being controlled by something else, then redundancy meaning that maybe you could have two algorithms, but both can go wrong, and then the redundancy that ensures still this.
So it works in fault tolerant. So any system which is fault tolerant, it is the software. Like you look at the aircraft, fly by wire. It can take off, it can land. But the question is whether we'd like to invest it on a vehicle for a normal consumption. That's a economic or business question. But whether the software and the hardware can do it in synchronization, answer is yes. I mean, look at the aircraft.
No, that's true, but then our regulation has to be adjusted.
That is why I asked that if somebody could highlight on a formal methods which are used in aircraft and fault-tolerant systems or fail-safe systems. There are different types of systems. How do they work? Hardware is controlled by the software. And how do they test it to make sure that it is 100%? 100%.
So this formalism basically, at least from an automotive perspective, at least Infineon would be compliant to ISO 26262. We have a formal calculation of fit rate, failure in time. And there is a defined standards already on this metric to gauge how good, the levels of the product. And all the way to the car level. And that's where this redundancy also comes into picture. I mean, somebody out there who's the OEM who's making the call on how much they want to invest in the redundancy of the system. And they go to the next level with respect to that. So, addressing some part of that, but regarding this fault tolerance, right? I mean, we need to have this standardization, and I also have to have a legal framework, and this is where universities also come in. I cannot just go out, or any company cannot just go out and say, okay, my modeling is perfect, or blah 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 is perfect. So standardization plus also certain legal framework, because who is going to bear the liability of an autonomous driving car, right? I mean. Yeah, so who's this? Is this the software developer, or is it the OEM, or is it the road, the government? So both standardization, legalization, two aspects to this, and that should be the overarching framework. And I think ISO standards are 26262, 1434, automotive safety, security. These will establish certain baselines here. We'll address some of those things. But I'm also trying to borrow the learnings from what we have in the smartphone, consumer industry, which is where we have this, how many times we have our OS and apps updated, I'm sure every week, right? So this is how your future transportation systems will be, or will need to be, because like what I said, agility is important, and these are at this point going to be connected, fairly complex systems. And if we completely use the consumer area, how they are doing, like randomized updates to the OS, and it's not going to work, simply. So there has to be a standardization there as well, so that different vehicles have a, need to have a vehicle-to-vehicle communication or certain fault tolerance built into it. So it becomes very more complex, and that's evolution. I think we are just at the beginning of this journey. I would not say we have realized the entire thing, but I would say I see some activity definitely with respect to standards. Legalization, some countries are ahead, Singapore is ahead, but some are, trying to catch up. But this is where we are, I think.
Yeah. Sorry.
I have a fault tolerance system and not really faultless system.
Yeah, it's exactly.
You understand the difference.
Yeah. And that's why I'm saying it's not faultless. So if there is a fault, standardization, legalization is the problem.
Yeah, we have diseases still will survive. The normal life expectancy is 70 plus years for Indians. But if you look at from the statistics point of view, our probability of living is zero.
So the point which I want to make is fundamental issue on these things is specifications. So because so many things are coming together, right? You asked the question about how we guarantee, right? So you can only guarantee what you know. correct? If nobody will release a product with fault, right? Deliberately release a product with bugs and other things. So the underlying fundamental issue is specifications, and the challenge which is coming now is that there are so many heterogeneous domains coming together. The language in which an electrical engineer will specify specification is going to be different from computer science engineer is going to be different from, and we at the base get reduced to writing some English level documents which nobody wants to write. It's all in the heads, and that's where the things get mixed and all basically.
Trust me, I mean, this requirements and atomicity of these requirements is the Achilles heel in this entire thing. And you're exactly right. I mean, different domains and the system view. If you're building a car, let's say the car is the system, and then deriving the top-down requirements is specifications and then the requirements is the formal approach to solve this problem. But then I think there is only a little bit of training again.
I mean, culture or languages have evolved.
Yeah,
There's no way to explore common kind of language specifies which can be commonly understood by.
But there have been recent advances in that formal, markup languages and other things to capture it.
Have their own things.
Yeah.
I mean, we are trying.
We are trying, yeah. But we are at the start of the journey.
Yeah. I would like to bring another dimension into this discussion. So we talked about functional safety and the formal process going through the ISO 26262. And there are methods and standards, and also regarding, we have to start it from the requirement engineering. We have, of course, to deal with systems that will fail, so we have to, plan for the failure, and that is, of course, an important aspect of that. Now, the other thing we need to think about more and more is cybersecurity. So the systems will not only functionally safe, but they might be attacked. And it's also from the methods and standards we have there a different type of thing. How do you deal with that in your day-to-day work with systems that have to be both cyber secure as well as functional safe?
So there is, Roland, there's an upcoming standard which is ISO 21434 to address this from a standardization perspective. But again, it is, I would say, analogous. Maybe Mithilesh can add here also from the software side what we do with Infineon, but it is analogous to the functional safety flow. It's ultimately a requirement-driven flow. Requirements themselves derive out of specifications. Okay. And nothing is perfect, but having said that, this is the most formal approach where you can map every requirement to analyze it, figure out where the threats are, threat modeling, and the complete formal analysis, and then verification and validation of that, and then closing the loop. So you go through the full V cycle. But yeah, I mean, this standard is just going to come up in the next, or going to be implemented in several, us and the competitors pretty soon.
So, sorry, what is the standard about?
ISO 21434 is cyber security for automotive. So, and it's analogous to 26262 for safety in automotive, like functional safety. So this would be the approach, Roland, at the high level. But I mean, when I get down to the aspects, I mean, slightly more implementation aspects, I think the main touch points are the hardware-software partitioning when we get into this. Because we're talking about this fault tolerance or, certain vulnerabilities, how we want to do it. And this is what I think also what Mithilesh's earlier question is. How do we reconfigure the systems so that they are less vulnerable over a period of time? We are getting into that domain. So the systems that we build now have to be having that potential to reconfigure themselves to eliminate certain vulnerabilities that may occur in future, post-quantum, if some of you may be thinking about. So, yeah, I mean, this is a challenge. I don't think it is addressed, but again, the standardization would help through the flow, at least the process.
So I have personally, I don't have too much experience with cyber security, but when I think about the problems of cyber security, when we boil it down to at the level of software, it's difficult, or even the level of reasoning about a system, it's difficult to differentiate. The main differentiation I see between security and safety is that in security we have to assume a active an active opponent in some sense, who is actively trying to attack the system. That's a main difference. Right now, I guess in many of the cases we have the traditional approach has been design, development, validation.
Yeah.
And that's something that is, I would say, the foundation. We have to do that. Now, on top of it, how do we bring in some of the system aspects? So when we talk about this, we end up, at least in terms of the design, development and validation, a typical approach is a reductionist approach, where we break it up and we treat systems in isolation. But the moment we come to security, you have to bring back the system view of it. We have to figure out the system, how the systems interact. And there are solutions, there are approaches. Systems thinking has been an engineering approach, right? I mean, it is a discipline started in World War II, and it was successful. It has been successful, it has had its place. I don't see some of those. Okay, so coming back to academia, one other thing that I would love to have students have an understanding of is, hey, what is systems thinking? What is systems engineering? What are the basic concepts that it provides, and how you can use that for reasoning about systems? So if we have that, then you will have a new generation of people or engineers who will be able to take that forward and really solve some of these very difficult problems. Okay, so that aspect is something that I would love to see. I would love to see a course on in more general terms. Maybe it's a specialized course today, maybe, but some of the ideas are very simple. So many of the basic concepts of systems engineering and system thinking are box and arrow diagrams. I mean, as simple as Automotive. Okay, so we should teach that.
Can I make a statement? Sorry. The thing is, I make this statement quite often, is that most of the doctors treat the symptom. Few doctors treat the disease. Nobody treats the patient. And it is important today because treating the symptom used to work for hundreds of years when infectious disease, leave COVID aside, was dominating the world. When I was born, the life expectancy in India was 34 years. Today it is 78 years because we have non-communicable diseases. In non-communicable diseases, you have to look at the patient at the system level, which no doctor does. That's a very, very complex system. If you have diabetes, they will give you a metformin without caring whether it is going to affect your hypertension or other diseases or the multimorbidity you have. So system level is the answer. How we look at it, that's definitely for all of us to debate. How do we look at the system level?
Just to complement what everybody said, the way this cybersecurity is being handled today, so it had one is the system level thoughts. So it is expected not to expose both systems to the outside world. So there is a piece of the systems which is going to communicate to the world, and all your internal systems remains to be internal. As you already showed about the number of buses into the system, not all the buses is going to be exposed. So this is central compute which is going to interact with the world, and you have to make a threat tolerant just for that central unit, and the other units will remain local. That's one part from the design side, looking at the system perspective. The second part is supported with the standards, that how to prevent the threat. So what kind of threat can come and who takes care, what the semiconductor company will look into, what the OEM is supposed to look into, and how it fits into the development process as an inherent chip. So both these points are being addressed today. One is the design part from the system point of view. where the direction is very clear that most of the OEM has already taken a call not to expose the whole system, part of the system which is going to interact with the rest of the world. Second is that all this, the engineering and development part, where this 1.434 is clearly giving the guidelines that what to do, same like ISO 26262, what exactly to be done during the development process of both hardware and software.
Yeah.
I think the point which I want to make is more relevant to this workshop in software engineering. As I've seen the automotive system evolving, right, over the decades, I think you started with monolithic ECUs, then you went to distributed things, and the industry came to a level where they needed standardization. So AutoSAR came in at that point, right? So that's a place where I think first time formalization of so-called component-based software engineering is coming. The software engineering course has, we have been teaching component-based engineering, but automotive system has an illustration of component-based engineering. So similarly, as you think security aspects, what are the extensions of that component-based framework to accept security? It's also software issue, right? Software modeling issue. The kind of points which I said. What are those boundaries being drawn in? What are the formal interfaces which a software should expose, right? Which are secured interfaces, some interfaces cannot be secured. All those things have to be written in terms of, there has to be a language in which you can specify at the software architecture level itself. I think that's more relevant from the academic research as well as the standardizations.
Yeah, thank you. I would like to now look at one more aspect, because we have also Kalyani Modi with us, Mr. Sanjay Kulkarni and Mr. Chandra Uber. Electromobility, we talked about that, also this transformation process of Volkswagen massively towards electromobility. What is the impact on what we discussed right now, software, functional safety, cybersecurity, because we have this massive move from the combustion engine to electric drive?
Yeah, so far we have been discussing about one side of the coin, and I think this industry is being triggered by two revolutions at a time. So this electromobility, or basically transformation to more electrification, is in a long term very positive thing. The advantage is that I would say a lot of the sensor actuator systems are now into one domain, which is electrical or electronics based. At least to a significant extent. So that may simplify to certain extent the traversal of domains, especially when compared to IC engine car. But that also complicates the functional safety and security because of the increase in the complexity in the kind of electronics that go into the car. Especially when you're talking about battery electric vehicles or hybrid. There are a lot of scenarios where you would have to protect the passenger or the car itself now. When you do the formal analysis, that you have to build in systems that are going to ensure that fault tolerance capability. So yeah, it may show up in terms of an increase in cost, maybe from Kalyani and other places where I think for more aggressive terrains, it's a different problem. But for passenger vehicles, it's a different problem. But please keep in mind that moving into completely an electrical domain or electrical electronic domain, end-to-end architecture for the car will help simplify in the long term. It will make it much more easier to give the over-the-air updates, make it also more transparent to the user on what is going on in the car, again akin to a smartphone. But it's a double-edged sword. That means if you make this a lot more better, at some point your safety and security are going to be in a trading off region. So more information means more vulnerabilities that you expose, is what Mithilesh was also saying. So this is an area of good research also going in. I think it is not a scenario where safety ensures security. At some point, you would actually reduce it to saying, adding more safety mechanisms in place may be counterproductive for security of customers. That's it.
Just to add, when we looked at the traditional IC engines, they have been evolved over years, decades. So the refinement happened. I think the slide what Roland showed. For example, in 1980s you had maybe one monolithic ECU and maybe one bus, and now you have hundreds. So it evolved over a period of time, whether it is safety requirement, functional requirement, regulatory emission requirements, all that came together and then it got evolved. So safety, comfort and performance, all these three were the order of the day. Now, when it comes to EV, I think one is the industry itself is getting cluttered. You see it in two-wheeler, three-wheeler startups. Anybody now, you go through Google, you do some Wikipedia, and then you can call yourself as a EV manufacturer. That's the reality today. Okay. Or you buy a few things and then you try to put them together. It will work on maybe one vehicle, two vehicles. Not all the scenarios are anticipated, not tested. This is one situation where the industry is today going on. On the policy makers also having absolutely no clue what is happening. So suddenly there will be one scooter gets burnt and then immediately there is a knee-jerk reaction. So for example, 2 days before a new regulation on the battery packs has come. As per that regulation, it's a standard gazette notification, it's not the draft notification. So we are trying to talk to all the industry operators. Okay. Nobody is aware of that regulation and then suddenly it is forced. The regulation calls for in less than 1 month. So from 1st October, you can't buy your electric vehicle because the battery pack is not certified as per the new requirement. So every cell needs to be tested for 5 cycles, C/3. Okay, and this has to be marked, barcoded from the manufacturer. Now, who are the cell manufacturers in the country? Nobody. Everything has to come from China or Korea, Japan. So the government is expecting in 30 days time, the global cell manufacturers who don't care about India, because the India volumes are not at all significant, they will make the process change in their organization, make the cells marked, and then they ship it out to India. And the Indian pack manufacturers certify for IP67, functional safety, and fire safety, UNEC, Rec 100, all those testing has to happen in the next 20 days time. And the BMS should incorporate RFID, which was not there until now. All the people are communicating the state of health, state of charge, etc. The battery condition monitoring is happening through either Bluetooth or through CAN bus interface. Now they want RFID. Okay. Now all this is expected. And now we started talking to ARA and ICAT. Now, okay, we have our pack. We also make our pack. We said we are all ready for this. Can I send my pack today and get it tested? He said, no, we don't have a test setup yet ready, so don't come to us for next 10 days, we'll tell you how to do it. So I think in this area of electrification, the challenge what I am seeing is at the academia, whether the people are getting prepared for that kind of a fast track, hockey stick curve in terms of electrification, point number one. Whether the industry is getting ready to get into those robust measures, whatever we are talking of functional safety or X-ray, for the, I think maybe some of the members here agree, disagree. Formal testing and certifying agency in India for ISO 2627. Okay, there are consulting firms. Okay, there is no way you can get a certification here. Okay, so even ARA say, okay, you go to Bosch, you go to Conti, or you go to maybe Infineon, etc. They can help you in verifying your systems. DUV do some consulting, but there is no certification agency. So our preparedness as overall as an industry is still, I would say, in a very, very primitive stage. So if that is not addressed, then we will have all these problems. Yeah? So for example, yesterday Gadkari made a statement that I will start fining the moment you don't put the rear seat belt. It's an awareness problem.
So I think I have a suggestion for IIIT. I was in India just a few months back. And I actually went to the produce BIC, or Battery Innovation Center, complete testing and certification center on our own roof. In fact, I saw the entire Tesla battery test bed being tested. I think already I have talked to the director of CMTA, who was interested in actually setting up such a center in Bangalore. That's something that you can think of. And the government of India is also interested. And if you wish to, you can just look at the website. There's a phenomenal testing facility that has been put in place along with academia. And every single EV from US gets through that center for certification. I think that's something that it could be a good option as a part of the strategic initiative to have a DIC. And they are ready to collaborate with the Indian institutes as well, because I spent an entire day at that center. One of its kind if you wish to, I can link you with
Yeah, thanks for the input. So I have to look a little bit at the clock. Unfortunately, time is flying again. But I think we also have now really good input for our working groups and breakout sessions, because the best is when those topics come from our discussion. What is really, what you're passionate about, what you would like to have addressed. But I would like to close the panel with just, one more question posed to the panel itself, open also for the discussion. And again, coming back to this example of VW and the electrification strategy, VW had this brand name CARIAD for bringing in the software division, but it has not been so successful yet. That's one of the reasons why also LLDs had to go, because they promised we will have 10,000 people in software soon, and then they work for VW. What makes it so difficult now for the OEM side, automotive OEMs, to recruit software specialists and then have them in their organization like this? So why a company like VW could not get these 10,000 software engineers so easily? What's your thought on that?
You want to start? Okay, so let me speak as the most ill-informed person in the panel regarding this. So my point of view would again go back to the same thing, that it's all about preparedness, and a cartoon was taking birth in my head. Let me just verbally say what it is. I see a little boy or a little girl, doing PyTorch and pandas and one of those machine learning algorithms, libraries, and then these demons are looking down at him. Security, one is safety, functional safety, one is regulation, one is high performance and whatnot. These are all demons which an industry vertical like this thing has created, Automotive has created. And I think our students are absolutely ill-prepared to, leave alone fighting with them. They can't even negotiate with them. So, if time permits, I'll probably draw that cartoon. But that kind of sums up in my head what is happening right now. And I will take my academics privilege to say something very unfashionable, I would say, So I would say we probably, I'm sure nobody is going to take this. I think we need to slow down a little bit. Okay, so both from the industry side, but definitely from the academic side. We keep saying that it's now a kind of a bad word or a curse word to say, why are you reinventing the wheel, right? So these days, we have so much information available everywhere that our students are, even for writing a Hello World program, they need to look up on the internet. And the only thing that they really need, they really are learning, because things are moving so fast, is, they first do a Google search and find out if something is available. I think we should do the unfashionable thing of learning to reinvent the wheel again. Mm-hmm. Which basically means to say that we should, try to go back to the basics, slow down a little bit. That's the message that I would say. That is the only way we are ever going to have engineers at the entry level, who will be able to talk to these demons that we have created. Otherwise, all of us are going to go the Volkswagen way.
Yeah.
Where are the engineers who will be able to handle all these things? And of course, industry is only bootstrapping over the available manpower. So that is one thing that I would say. And another point that I would like to make is, look at the plethora of ideas that are coming in, from representatives of industry. So, we have heard from industry a lot. Your engineers are not employable, which is true, which is absolutely true. But I think we should really have another workshop where we have all the representatives of industry and let them fight out on a definition of employability. I don't think that they have a lot of agreement on that. And that's the reason why for many of them it means basically the selected set of tools of their choice. Okay? So if somebody is working on machine learning, they will want our students to learn machine learning libraries, not machine learning theory, not the mathematics part of it. If somebody is working on web development, they would want them to learn Node.js, Angular, blah blah. Who cares about theory of computation? Who cares of formal verification? Who cares of logic? Cares about mathematical logic? But I think somebody has to come back to the basics and say, okay, go ahead, take your time, learn mathematical logic, learn programming language theory. I think unfashionable point of view from an academics.
Sujit, I think you're being too harsh. I can tell you because I was in industry and I came to IIIT to teach lattice theory. And everybody said, oh my goodness, I don't understand anything. It is so boring. Now, coming to your point of what the challenge is. I'm not completely familiar with the travails of CARIAD, what actually happened there, but I do know that building an organization is not an easy job. It's extremely difficult. Collecting the set of people with a shared, it's not about just, okay, we have got engineers, let's put engineers together, they'll solve the problem. That never happens. It's a human endeavor. You have to have a shared vision, you need to align, and aligning people takes time. And it's extremely difficult. I can say, even building a group of 10 people who are able to succeed in a company takes time, effort, lots of effort. We have seen companies, I've heard of companies, for example, Uber was doubling every 6 months. I don't know how they managed. And some of the people who managed it have written books saying that, okay, what they managed, how they managed it. But I do know that building an organization which is effective, which is delivering, and which is living up to its potential is extremely difficult. That's the only thing that's the only thing I can say about Volkswagen's experience with CARIAD.
Roland, I have spoken too much. Can I make one statement? If you look at a symphony, a lot of time you will see the number of musicians are more in number compared to the people in the audience. So let me take that example. There is one maestro holding 2 sticks. There are 200 to 300 people playing the same harmonic. That's one message. The maestro makes sure that everybody is playing the same harmonic. They are not playing in their own free will. Message number 2. Maestro turns his back to the audience, which we never do. After the symphony is over, he faces the audience, accept the power. So if you take that as an example, our role is that maestro. If Volkswagen would have done that, they would have been successful. They did not do that. That's all what I want to say. Thank you very much.
Just to add one very important point in this discussion. See, even today, this developing the automotive software is still very different than the rest of the application area or the consumer and the iOS application. And the reason behind is that if you are developing a productive automotive software, the cost of the verification, validation and process compliance is 80% versus your design cost of 20%. So you are writing the code for 20% of the time. The rest 80% is going to make it productive. And the reason behind it because you are constrained with the standards, with the compliances, with the processes, and you have to follow this project. Now this requires a very different mindset. You have to have a different kind of engineers to really stay and work in this kind of environment. If you are free-flowing academic students, that person never like to do that because you like to write 90% of the times different kind of programmings and run it on maybe any systems and see the results coming and that's it. But once it comes to the productive software for automotive, it's a completely different game altogether. And this is where you need a different kind of people to hire, to train, and then to keep it into the system. You might get engineers very easily for the Googles and for the iOS development, but not in the automotive world. It's not that easy still even today.
Actually, just seconding to what Mithilesh just said, I think Mithilesh, if you remember 3-4 years back, not at the scale of what Volkswagen faced, but we were also having a lot of trouble in hiring in this very niche area people. I mean, not obviously thousands of people, but even tens of people. So we had a thought experiment, basically like, okay, well, why not we have tried, going to premier institutes, hiring people, and they all wanted, some people just wanted to do financial engineering or something else. So like most people now do, right? I mean, most bang for the buck varieties. So we ended up, I mean, after some deliberation, we thought, okay, to our scale, we thought we would go to some premier institutes, do hackathons. I think we did it in few places. We didn't ask the students what is their CGPA. First thing, we said, okay, no bar, okay? We are not going to say limit is 60% or 4.0 or 3.0, something, nothing. Just come in. We have given 2 or 3 problem statements in the first one that we did. I think recently we did it in another place. And whoever is the hiring panel, we just asked them to stand in the corner of the room or somewhere, observe the 5-10 teams, 30 students, tackling a small algorithmic problem. Okay, let's say. You can, I'm sure anybody in this room will be able to define simple problems that you can solve in 3-4 hours. In about 15 minutes, the panel was able to identify those 5 people who stand above the rest. 3 of them are not the toppers. Very mediocre CGPA. We have hired them. They are doing excellent in the company now. And that's what he was saying, his mindset. The way we grade the students is completely faulty. I think the university has to, because academically you have to make sure the GPA is, ultimately say pass and fail, right? So, but that's okay, that's expected. But from an industry point of view, especially, I don't know how to scale this to thousands of people, but I can tell you that had worked wonders. Those people who have now know and understand, okay, I am here to solve this problem, and all what we have told them when we had is, you'll be working on something similar, not exactly the same, something similar, it's teamwork, and you will be challenged every day, but not on the same area, but on a different, area. So with that, I would give you
wonderful. Wonderful.
Thank you.
Thanks. So with that, really wonderful remark for, making all of us think what really is, how we kind of find the right talent for the companies and keep it in the companies. I would like to close the panel. I would like to thank the panelists for this very lively discussion and for bringing in your points. And it was a very easy job for me because I could just let the discussion flow because you came up with a lot of thoughts and ideas yourself. I would also especially thank the audience, the delegates, here because you really made that very special discussion because of your questions, because of the interaction with the panel. And I think we have now a very good setup of potential questions for our workgroup sessions. Because of the timing, and as you know, we would like to also close the workshop not too late so that everybody can safely go home. I would suggest that we just have a little bit, you know, let's say 10 minutes more time for the workgroup discussion than originally planned. And we would, whenever a workgroup is ready, go for lunch. It starts at 1 o'clock, so don't make it later than 1:10 for going up to the lunch, because you could continue their workgroup interaction also during the lunch break. What we have to do, of course, still is we need to define the topics of the work groups. As you might recollect, we would like to, you know, kind of have a set of discussion topics that the different groups would like to address. Then we will allocate the rooms, and the breakout rooms are here in this building. You will be guided to the breakout groups. You can meet the work group session members, discuss the topic, and after lunch, we will ask one of the speakers of the different work groups to just summarize your findings. Not a long speech, but a summary of the findings, because this we would like to use for then also to kind of strengthen the networking beyond the workshop, because these topics will be the ones that will be interesting to you and could also trigger furthermore discussions. Okay, so once again, a big thank you for my fellows. Thanks for the audience. And please come forward here and suggest your topics. Nominate one who would like to lead the work group, and then we will go for the breakout sessions. And 1 o'clock the lunch starts. You can take a little bit more in the work groups, but please not too long, because we will anyway come back and then discuss our topics.